Now, finding asymptotes is all well and good. Even the vertical asymptotes. Great, I can find vertical asymptotes. But we have to keep an eye out for when there might be a hole instead of an asymptote. And the way to find that is a hole occurs when a value, a real number that is, whoops, I didn't mean to erase that. So here, a real number there, the value for the variable, God, my bad handwriting, sorry, variable makes both the numerator and the denominator equal to 0. So that's the one caveat to this. So you have to always be on a watch out for a hole rather than always assume that it's a vertical asymptote. So in this case, how do we find that? Well, the easiest way, if there is a common factor, x minus a, in both the numerator and the denominator, there is going to be a hole at x is equal to a. So we're going to factor and look for them. Once you found a, by the way, to find the corresponding y coordinate of the hole, reduce f of x by canceling out the common factor and then substitute in x is equal to a to find the y coordinate. So let's try that. So it says find the hole if any of the following problem. So the way I check if something has a hole is I'm going to factor. So the numerator is going to be x minus 3, x minus 2 over x minus 3. Oh yeah, we have a common factor. That means there's going to be a hole at x is equal to 3 because I take the common factor x minus 3 and set equal to 0. That's where the hole is. Now, once I have the hole, I could essentially write f of x is equal to x minus 2 as long as x is not equal to 3. So those two are the same thing. But f of x is not equal to x minus 2. It is actually equal to this whole thing. Because if I was to draw this, even if you look at the graphing calculator, if I drew it without the hole, it would look like this. At -2, so we would have a graph that looked like that, right? It's going to be linear, slope of 1, y-intercept at -2. But that would be if, for example, the function was y is equal to x minus 2. But it's not. It's this whole rational function. So how do we account for that? Well, the whole tells me that when x is equal to 3, there needs to be a hole in the graph. Like I have to actually draw the hole in. So how do I find that? Well, I reduce it here, and then I find and substitute in the 3. So it's going to be 3 minus 2 is equal to 1. So that means the hole is going to actually be, the hole is going to be the order pair 3, 1. So that's here at 1, and that happens here at 3. So you need to draw those things in. That's super important. So let's look at the next one. Does that, if I factored that, is there a hole? Yeah. Plus 2x plus 4, right? It's the difference of cubes. X minus 2. Yes, we have a common factor. So the hole happens when x minus 2 is equal to 0. So that's x is equal to 2. So we have a hole at x is equal to 2. To find the corresponding y, look, I reduce it and substitute it in. So I'm going to have 2 squared plus 2 times 2 plus 4. That's me substituting it in. Oh, whoops. Undo. I didn't mean to erase it. I meant to highlight it like that. That's just substituting in the x is equal to 2 for the x in the reduced version, right? So then we get 4 plus 4 plus 4 is 12. So then there's going to be a hole at the order pair 2, 12 for this. And this happens like what's left over once I look at this is actually a parabola. So the graph of this would be a parabola facing up. Like, I'm not really sure. It's 2 comma 12, so it's probably going to look somewhat like this. The vertex would be over here. And then up here on the parabola, there would be an open hole here at 2, and then up there at 12. Because what is left over once I reduce this a parabola? That's finding holes.